In this video, I'm going to talk about path independence. So path independence is one property related to the line integral over a vector field. In the previous video, I talked about the line integral over a scalar field and a line integral over a vector field. So line integral over a vector field typically will depend on the line we're talking about. For example, you give a vector field. Okay, if I give it a vector field vxy, for example, I give it a line which is represented by r sub t. Here I'm only using 2D as a simple example. You could also apply this to high dimensional case. So t is from t0 to tf. So if I'm talking about the vector field and also I talk about the line s given by this, so typically, if you do the line integral from t0 tf and vxy and dot dr, basically, okay. Now I have it depends on actually the s we're talking about, we're given. So for different s, we may have a different result, even if we have the same starting and ending point. Okay, so here I give example showing, and what case is, it doesn't matter where you get a start, what line you're choosing. It just matters that the starting and ending point. Okay, this is called path independence. Okay, for example, if I talk about the v xy is given by x and y. Okay, this is my vector field, and s is given by r t, which is t and t squared, and of course t starting from 0 to 1, which means, hey, I'm starting from 0 0. If I'm drawing the line, this line, the line is just given by this line. It's just starting from here and I take a curve and go to 1 1. So the starting point is 0 0, ending point is 1 1. Okay, right? Because this is how we compute the starting and ending point. If you do the line integral as over the vector field, which is integration from t to 0 from t to 0 to t equal to 1, so v dot dr, which is line integral over vector field. So this is dot product over here. Okay, so what I do is, remember here v is xy, so v just given by xy. Remember, I have replaced x by xt, yt, right? Enough. So this x is xt, right? What is x? X given in my line, which is given by t. So this is the xt, right? Yt. So here for r, because rt is xt, yt, right? Basically, you have t, yt is 2t squared. That's it. So replace xt by what's the representation in the line, okay? So which is xt yt, of course, because xt is t, so replaced by t and t squared. And also here I have to compute r dot t, which is x dot t, y dot t. So x is t, so the derivative is 1, and derivative is 1, and y dot t is yt is t squared, right? So the derivative is 2t basically, right? So you have 2t, 1 and 2t. Then you integrate that over dt. So you actually convert this one to a scalar integral. Then if you keep on computing the dot product and do integration, what I end up having is, oh, my result is 1. So I just omit all the intermediate steps. You can follow the computation that they did to figure out why the result is just 1. So the result is just 1. Okay. Now let's pick the same vector field, but I'm going to pick a different line. Of course, with the same starting and ending point. Starting point is still 1 1 0 0. Ending point is still 1 1. So what I'm going to do, I'm going to say, and pick another one, which is straight line, which is this line, which is the purple one. Okay, starting here and ending here directly. So my line is just be given by t and t. So different previous one, xt is still the same t, but yt is become t also. So of course the starting point for the t is 0, ending point for t is still 1. If I follow the same step, which is v is xy, which is the xt yt, so now here xt yt, they're the same, they're all t, so it's tt, and r dot t, I have to take the derivative of this t and t over dt, so I have 1 and 1. Okay, if I take the computation, you can see it's the same, it's still 1, also 1. So which means they have the same value. Okay, so it doesn't matter which line we're selecting, it looks like they're pretty similar, they're the same. So this problem is called path independence. In other words, the vector field determines if the line integral changes with respect to the selection of the line, which means it doesn't really matter what line we select. it's always the same for that vector field. As long as given a starting ending point, it will determine the value. It doesn't matter which line we select. So this property is called path independence. Okay, path independence is important because a lot of times, if I give it a very complicated path, for example, here, I could give you a path somehow like this. If I give you a path like something like this, I'm going to do a very random path right here. So starting from 0, 0, ending with 1, but I'm giving a really, really weird path for you to calculate. So this is my S. Okay, if I want to compute T0, Tf, I'm going to V, X, Y, dr. So you know how complex that will be to compute this irregular line, because it's really difficult to compute that. However, if we know that it's path independent, I know, I don't have to compute this very complicated one. I only need to calculate select a very a simple one for the computation, which means, for example, I can select this starting from this point and ending this point, which makes my life much easier. So that's the value, that's important why we consider path independence. Okay? Then, since we're talking about path independence, we want to see what property we need to guarantee that the line integral over vector is indeed path independent, which means it indeed does not depend on how we select the line. Only matters is the starting and ending point. Okay? So here's the definition of the path independence. So a vector field V that satisfies the property that the line integral over that vector field is independent of the line, but only, of course, depending on the starting and ending points, is called path independence. Okay, which means the vector field is very important. It's not as a line, because it doesn't matter which line. So the vector field itself, the vector field has certain property that guarantee that it's path independence. So if a vector field if the vector field can satisfy the property that the line integral over that field for any, it doesn't depend on the line, only depending on the starting and ending point, that field is called a conservative field. It's called a conservative field over here. What we are interested in is knowing what property can guarantee that a vector field is a conservative field. Then we can apply the path independence, meaning that if we want to compute the line integral over the field over a vector field for some line, for some complicated line, we actually can simplify quite a bit if we know it is path independent, or if the vector is a conservative field. Okay, there are actually three properties we can check, condition we can check is a vector field is conservative. You can apply any of the three. You don't have to check all three. If any of the three conditions is satisfied, then it is a conservative field. Okay, the first approach is called a gradient approach. Okay, what it basically says, if my vector field can be written as the gradient of a scalar field for some scalar field fxy. Let's say this is only for 2D, of course. You can also have for high dimension one. Then this field is a conservative field. Okay. For example, if I do V is xy, is x, this is my vector field, right? This is my vector field. So I can say this is the gradient of some scalar field. If I take a gradient of my, let's say arrange my function is x squared divided by 2 plus y squared by 2. This is a scalar field, okay? Because for any point, you actually can compute a scalar value associated with that point, okay? If you take a gradient of that one, gradient is just you take a gradient of partial over partial x times I plus partial y times j. So check my video on gradient if you don't know how to compute a gradient, okay? So video on gradient. So it's just, if you do that, you basically have xi plus yj. So that's will give you the gradient field, right? So why the gradient field approach? Why this gradient, the condition will guarantee that this is a conservative field, okay? The reason being like that is, if I'm doing the integration of t to t0 and t to tf, vector field dot product dot dr is my vector, my line, okay? This one can represent because my gradient is given by, the vector field is given by the gradient of a scalar field. Of course, I can replace by gradient field, gradient times dr. The nice thing for that is, my gradient, this guy over dr is just exactly dfxy, okay? Then if you do that way, you can say, hey, my line integral over here over a scalar field is just be given by fxtyt evaluated at TF and T0, which is basically the scalar value evaluated at ending point. This is scalar value at ending point. And of course, this is the minus the scalar value at beginning point. Of course, you can see over here, because it only matters where the points are. It doesn't matter which line we select. That's why it's called path independence. Okay, there are a lot of reasoning why that's okay. Why is the gradient of this guy is equal to this one? I have put all the calculation over here. So dfxy over dt you can consider as dfx over dr and dr over dt. So this one is just be given by the gradient. Of course, this is just be gradient, and this is by dr. Okay. That's why if I do dxy, if we move the dr over here, so this just be given by the gradient. So I sort of can see why this guy, the reason that this guy is over is this one I already did over here, right? The gradient times dr is d of fxy. That's why that's equal. This one's coming from my analysis over here, okay? Showing why that's equal, okay? So as a matter of fact, you can do this integration of T0 TF of V xy over dr if V is a gradient of a scalar field of fxy, so which is equal to fx tf ytf minus fx t0 minus t0. So this f is, so here is Vxy is gradient of fxy. So that's required. Then I can have this, which means it's just equal to a scalar value for the ending point and minus scalar value for the beginning point. Of course, it doesn't depend on the line where we select. It only depends on the starting ending points. Okay. See, similarly for this one, is Vxy is the same as previous one, right? As I already said, okay, this V is equal to gradient of xy. The gradient is this is equal to 1/2 x squared plus y, 1/2 y squared, right? So according to what we said over here, hey, because this is a V vector field is a gradient of a scalar field. So integral, the line integral over the vector field is be given by fxy as the beginning point. At the beginning of when t is equal to 0. You can say also here is xt and yt and t equal to 0, of course. And this is xt yt when t is equal to 0. Okay, so you can just replace this one, right? So when you have this one, when t is equal to 1, my ending point, of course, right? I mean xt is 1 and yt is 1. So I have 1/2 x squared plus 1/2 y, x is 1, y is equal to 1. Minus 1/2 x squared plus 1/2 1, x is 0. So this is my beginning point. Okay? Alright. So it's 1/2 times x squared is 1 plus 1/2 y squared is 1 minus, of course, this will be 0, right? So it's 1. So which actually verify that, yeah, indeed, the integration of my the line graph of my vector field is 1, even I use this property, which is the same as what we computed at very beginning. Right over here is also 1, so they're the same. Okay. You can also sort of consider this one as a very for the potential. If you know the potential energy that for the vehicle, you basically say if I'm driving from A to B, the potential energy that you use from A point to B point doesn't matter. It only matters you can move around, big around. It only matters is your starting ending point in this case. It doesn't matter where you go. Okay, that's what you can also imagine. For example, if you drive along, this is my hill, for example. If you drive a car, of course, assuming that we ignore all the friction, all the stuff. If you move the car along here, right, move along the path, starting and ending point, it only matters starting and ending point. It doesn't matter where you go. You could go this way, right? And it always matters the starting and ending point. It doesn't matter the path. Okay. So this is the first approach you can verify if the vector field is path independent or is a conservative field. Okay. The second approach is called integration approach. If V is a conservative field, if integration is equal to 0 for every closed line. When I do the integration of this notation, I mean is the same, the line starting and ends at the same point. So you sort of have a circle. You're starting and ending at the same point. If this one is true for every closed line, of course, which means it's basically doing this, right? What this means is hey, if I'm going to do line from here, okay, this is my line, or I make it closed, make another one. So one is starting from A, let's say this is A, this to B, right? One is starting from A to B, one is starting from B to A. Of course, this will be 0, right? This will be 0 because you go back to the original point. You don't do anything basically, right? If this is true for every closed, this one, remember here, you must be able to have for every closed line. So this one typically is not very useful because you have to check for every closed line. It's not possible you can check for every closed line. So this is just kind of, you can imagine this kind of property we can say if this is a conservative field, rather than we can verify is conservative, because you have to verify this is equal to 0 for every closed line, which is unlikely we can check those. Okay, so typically people don't use this property quite a bit. Okay, the last point is called a curve approach. So this V is path independent of a conservative field if the curl is equal to 0, 0, 0, 0. Of course, when we say this is for a three-dimensional one, and the region is simply connected. I'll talk about this one in a few minutes. So here, this one applies to 2D and 3D. For 2D, you basically consider this V as V1, V2. You can add on one component, which is 0 for the last component, because you can add append last one, make it 3D vector field, because the curl can only apply to 3D vector field. So if you only talk about 2D, you have to make sure that you add a 1, 0 at the last component, and you check the curl if my curl of V is, for this one, is equal to 0, 0, 0. If this is true, and also its region is simply connected. Simply connected means I give a definition of this one. A domain D is simply connected if every closed curve in this D can be continuous shrink to any point in D without leaving D. So this is kind of really complicated from this is writing, but this is just for mathematical rigorous. Okay, what does it mean? What does it mean? Okay, so what it means, a domain D, let's say I have a domain D over here. This is the blue one, my domain. Okay, if it's simply connected, if every curve in the D, for example, I select a curve over D. Okay, the curve can be continuous shrink, so I can shrink it to any point. So basically can shrink to any point in this D. So I can shrink to every point in the D without leaving D, right? Okay. If there's no holes, if there's no hole, yeah, you can do it because you can shrink it to any point right over here, which is true. Okay. However, if I have a hole, let's say if I'm going to, this is my area, this is the whole area is a black area, but I have a hole. This is a hole. The hole is not part of this D, domain D. Now, if I select a blue one, let's say I select a blue, this is my curve, okay, this is my closed curve, right? I want to shrink it to this point, for example. So you basically shrink, you continue to shrink this point until this point. Well, you will leave this D because at a certain point you will sort of cut across this red one. The red one, because you're trying to shrink it. Continue to shrink it, but you will leave it because at a certain point you will actually end in this point right over here. Then you will leave the D because this D is does not include this red anyway in the red circle, right? So it's not you cannot do that. So this is called not simply connected. You can sort of consider this is a simply connected means no holes. Okay, right? It's no holes. Yeah. They are all most complicated scenarios. Especially for high dimensional one, I don't talk about that, but generally you can interpret this as if there's no holes, you can say this is a domain D is simply connected. So last one says, hey, you can check if your curl is 0, 0, 0, and also you check if the region has no holes, then it's also conservative field. Okay, so typically the last one is also a little bit limited because we need to compute the curl, right? So curl only applies to 3D, so which means you only can use this one to check if the field is conservative for 3D vector field, but not for high dimensional one. Okay, so generally speaking, the first one, the gradient approach is more popular. It doesn't matter what dimension you have, you can have a high dimensional one, but it's a little bit complicated. You have to find the scalar field, and you take a gradient of that scalar, it will give you the vector field, so which is a little bit complicated. Okay. So in this lecture, to generally summarize, let's talk about the path independence for the vector integral over line integral over a vector field. So which is important because in certain cases, if I have very complex line that I have to integrate, I have to do the line integral over for the vector field, which may not be possible. But if I can simplify this one by taking another line which doesn't change the actual value of the line integral, I can do that, and it can make my life much easier. There are three approaches you can check if the vector field is the integral is path independent, or we call it conservative field. One is the gradient approach, which is a very general approach. The second approach is the integration approach, which is not very useful because we have to check the integral, the line integral over a closed line is always 0 for every path. It's very hard to verify. The last one is called curve approach, which is also very simple, but it requires normally we can only consider the 3D or 2D vector field. Okay, that's all for the line integral, the path independence.